Good morning. So we're going to pick up a little bit before where we left off last time, just to include a little bit of review. The last topic that we discussed last time was the small signal diode model. And so in the small signal diode model, the diode is represented as a variable resistor, at least in one of the two circuits that we use, because what we do is we take the total instantaneous and we divide it up into the static and the time varying. Now, the essence of how this model is used is in the name itself. Small signal, right? This is only applicable for cases where we're worried about the effect of a small change in the voltage through across a diode. One good example is like the example that we saw or that we worked through, which was a voltage regulator. And that's a case where we are looking at the effect of small changes in the voltage across the diodes. Again, like what I just said. Now, it's not so good for examining applications such as a rectifier, right? Because for a rectifier, we would have the voltage most probably varying over a wide range, 5, 10, 15, 20, hundreds of volts. And that's pretty obviously outside of the expected use for this model. So the main takeaway, I think, from this section is how we divide the system up, right? Because we start off with a circuit that looks like this, which has both a time varying component, which we also call the AC, as well as a static component or steady state component, which we often refer to as DC. And that circuit is going to be split up into two different pieces, right? One part is going to be our static circuit, which is going to take the DC source. This resistor here is going to be the same in all three circuits. The diode is going to be what is represented differently. So here, we're going to use the constant voltage drop model, which means that we know this voltage will be 0.7 volts. Down here, we represent the voltage, the diode using a resistor whose value is set on one of the coming slides. So an important part of understanding how to use the small signal model is understanding how to take a larger circuit and split it up into the two different pieces. So I don't want to spend too much time rehashing what we had already done. I did want to point out one other equation, which is this right here. So what we see is that the small signal resistance is equal to the thermal voltage, which is normally between 25.8 and 25.9 millivolts, as well as the current through the diode that we determined from the static circuit. Remember that uppercase variable, uppercase subscript refers to the static circuit. So now I'm going to fast forward a little bit because, like I said, I'm not going to go through the whole example again. That's not really our goal here. I apologize for some of this. Unfortunately, it seems like the PowerPoint doesn't want to show all of the notations properly on my iPad. So what we'll try to do is get through it today, finish up this lecture, and then before next time, I'm going to try to come up with a solution to fix this. All right, so this was the example that we went through last time. All right, so the next new topic that we're going to discuss is a rectifier circuit. And we've talked about rectifiers already. We talked about a half-wave rectifier. So, like it says here, one really important application of a diode is a rectifier. It's an electrical device which converts alternating current AC to direct current DC. And it's a really important application because it's a major player in a DC power supply, like that which, connects your laptop to the wall or that which connects your iPad to the wall. Now, it can be broken up into several different pieces. For a DC power supply, the rectifier is one part of the equation. So what we're going to do is we're going to look at this going from left to right, and you can see each one of the steps is outlined here. So we start off on the left-hand side with an AC wave, 120 volts RMS, 60 hertz. Looks like this down here, and this is similar to what you would get out of your wall socket. The first step in the process is going to be to use a transformer to step down the voltage. Now, how does a transformer work? I'm not going to go too much into the detail of that. Essentially, it's a pair of magnetically coupled coils, and by setting the ratio of the number of turns, so if we call this N1 and N2, okay, number of turns over here, number of turns over here, or number of coils, we can determine whether the transformer steps up or steps down the voltage. So let's say we step down the voltage by a factor of 10. That would take the 120 volts down to 12 volts RMS. Okay, but it's still AC, as we can see right here. Okay, this little snippet corresponds to the block saying diode rectifier. So a diode rectifier takes us from here to here. Okay, this is a full wave diode rectifier as shown in this example. A half-wave rectifier, right, would give us something that looks like that, where there would be a missing, the negative half of the cycle would be simply zeroed out. Now, this right here is technically a DC wave because it doesn't cross the x-axis, but it's still not going to be something that we can use to charge our laptop or to charge our cell phone. The next step in this process is going to be to try to filter out the ripple. And for that, we are going to use something we're very familiar with, which is a low-pass filter. And our hope is that this will reduce the ripple by 90%, leaving just 10% of our ripple up top. Now, the last piece of this is the voltage regulator, which is essentially what we looked at in that last example from last class. And that takes us the rest of the way to completion. So hopefully it flattens out that 10% ripple and gives us something that's completely flat. Now, is it ever going to be completely flat? No, right? Sorry, one second. We'll always have some small ripple, but it should be good enough to allow us to charge our devices or whatever application is required. Lastly, what we have here is the load, and obviously the load is what's going to use the power. Okay, so the half-wave rectifier we have already taken a look at. I think that was in the very beginning of the chapter. But we'll quickly go over it again here. The half-wave rectifier uses only alternate half cycles of the input sinusoid. And so as you can see in this picture, right, you end up with an output that looks like that. It's flat during the negative part of the half cycle. It's composed of a single diode. And it's the operation is pretty straightforward. If you look at the input waveform, which is shown in black, and the output waveform, which is shown in blue, what we'll see is that there is a difference between the peaks, right? Because we have to account for the voltage drop across the diode when it's conducting, which will normally be about 0.7 volts. Now, when we talk about a half wave or any diode rectifier, and essentially really any diode device, there's two different characteristics that we have to be concerned with. Well, there's multiple, but two main ones are current handling capability. So how much forward current is the diode expected to conduct? Right, these diodes cannot conduct an infinite amount of current. They will overheat. And then peak inverse voltage, PIV. What is the maximum reverse voltage that the diode is expected to block without breaking down? We've seen in some of the previous VI graphs for the diode that we do have a breakdown region. A diode may be able to withstand negative 5 volts, negative 10 volts, negative 50 volts, but eventually all diodes will reach a point where they'll break down and start to conduct in the reverse region. So now we ask ourselves, well, what models can we apply to analyzing rectifiers? We know that there's some that have good fits in certain applications better than others. Right, we know that for the voltage regulator, for example, the small signal model is a pretty good fit. Let's talk about potentially using the exponential model for this. So is it possible to use the exponential model to describe rectifier operation? Yes, you could, but it is going to require a lot of work, especially when you're talking about analyzing something in the time domain where you are going to have to do these calculations for every point along the waveform. So definitely would not recommend that. Now, what about the small signal model? Actually, sorry, I apologize. That's not what this is saying right here. This is another question. It's asking, so what about for small inputs? Will the rectifier work for very small inputs? Let's say the peak of this right here were only 0.5 volts. Now, if you look at what's going on, if this is 0.5 volts right here, and this is 0.7, that would actually push the blue all the way through the bottom of the graph, which obviously that doesn't make any sense. So if we're talking about very small inputs, the rectifier is not going to operate properly when the input voltage is small and below 1 volt. We're not going to talk too much about how a rectifier is used or how it reacts for very small inputs. It's not really a popular application. If you want to do it properly, you have to use something called a precision rectifier, but again, that's not necessarily a topic that we're going to spend a lot of time on. For our purposes, we are going to be assuming that our Vs is going to be greater than, let's say, 5 volts or so when we are talking about any problem related to rectifiers. Okay, so now let's jump into the next topic. Well, it's related to the first one, the full-wave rectifier. Now, a full-wave rectifier differs from the half-wave because instead of taking this right here and spitting out this, it will give us both sides of the waveform. This is advantageous for several reasons. One main reason is that you have more power output. And so what we can see here, this is one implementation of a full wave rectifier. This is called the center tapped design. And this is what the input output characteristic looks like. But we're gonna blow this up and take a look at it in more detail. Okay, actually I think I can, yes, I'll start here. So if you look briefly at the center tapped design, the circuit is composed of 3 or 4 main components. So you have your transformer, you have 2 diodes, and then obviously you have your load. Now what does this mean to center tap the transformer? Let's take an example. Let's say, first off, let's just assume there's a 1-to-1 ratio here in the number of turns. That'll simplify what it is that we're doing. That means that this transformer is not really providing any step up or step down. It's simply just providing electrical isolation and spitting out the same voltage that we put into it. Okay, so what happens when we center tap it? Let's say that here we have 10 volts RMS. Center tapping, without going into too much detail, is actually more physically, the term really physically describes what we're doing. You can take a connector and connect it to any of these coils along the way. If we clip it in the center, to make a long story short, we're going to end up with 5 volts over here and 5 volts over here. Clipping in the center divides the voltage by 2. So what we end up with is 2 voltage sources that look like that. Now, why is this advantageous? Why do we do this? Is because we'll see, as compared to later designs, it allows us to reduce the number of diodes that we need for this design. So let's take a look at how this works. Okay. When the voltage here is positive, showing the positive and negative polarities as shown, both Vs, both of these will have the polarity positive, negative, positive, negative. Now, when that's the case, this diode here will naturally block because it will be reverse biased, and this one here will conduct. And the result is current flowing through this path as shown. It will flow out through the transformer, down through the load, and then return to the source, completing the path. This part of the circuit will not be used, again, because diode number 2 is going to be blocking. So now what happens when the polarity reverses? So we have negative and positive. What happens now is that both of these voltages will be negative and positive, which means that this diode will now block and this one will conduct. So the current, even though it's flipped in direction, will still have a path to flow through, which will be through the transformer, through diode number 2, up and around, same direction, through the load, and then back to the source, completing the path. So the reason why we need the center tapped transformer is because that this design only works when we have two different sources, right? If we can't imagine this as having two different sources, then we would need more diodes in order to make this work. Now, to look at the input and output real quick, what you'll see here is that the output is in blue, it is fully rectified, and the difference here between the Vs and the VO will be, again, about 0.7 volts. And the reason for that is because when current is flowing, it's only flowing through one diode. So the drop that we expect will be that associated with a single diode. This is homework number 9, which I believe has already been assigned. If it hasn't, then I'm assigning it now. When I do the live session, I'll discuss a little bit more about how we're going to handle the homework and things like that. This homework, problem 432, is a good one. The reason why I included it in the notes in this form is because it's one that I've gotten a lot of questions about in the past. And so, as you know, I like to save some work for all of us. So if there's a problem that keeps on coming up over and over again, I'll try to make a really good version of the solution and post in the notes. So this is a pretty good version of this the solution for this right here. So I encourage you to take a look at it. You can combine it with the textbook solution that is provided. Okay. So what are the most important observations from the way that this full-wave rectifier behaves? Right, the most important thing is that it does rectify. The direction of the current flowing across the load never changes. For both halves of the AC wave, the current's flowing from the top to the bottom. The full-wave rectifier produces a more energetic waveform as compared to the half wave. And now, let's talk about this for 1 second. It's telling us that the peak inverse voltage for the full wave is 2 Vs minus Vd. But why is that the case? So let's go back here for a second. Okay, so PIV. Let's ask ourselves for a second. First off, there's going to be a different point at which the inverse voltage is applied across D1 and D2. Let's take a look at D1 first. So D1 is going to be blocking when the input voltage is reversed in polarity. And as you can probably see from the picture, the peak of that inverse value will occur at the peak of Vs. Now, let's ask ourselves, so what is the inverse voltage applied across that diode at this instant right here, which we can call T alpha? Okay, that voltage will be equal to so I'll split it up. We have from here to here is Vs. Okay, that's the height, right? We know that because it's dictated by the black line. From here to here is Vs again, but we're worried about the gap from here to here. So we have to step it down by this little gap, which we already know is Vd, or the 0.7 volts. So if you look at the gap from here to here is equal to 2 times Vs minus Vd, where this is 0.7 volts. So, and that peak inverse voltage is experienced at this point down here. So when we are designing a full wave rectifier that relies on the center tap design, what we see is that we need to design or choose diodes that are able to withstand that sort of inverse voltage. Let's say we're rectifying a wave that has a peak of 20 volts. So that means that our diode that we're using better be able to block 39.3 volts, because we have the 20 plus 20 minus the 0.7. Okay, now, moving on. There are other rectifier configurations, and another is called the bridge rectifier. Now, the main advantage of the bridge rectifier is that we don't really need this transformer right here. I mean, it's showing a transformer for electrical isolation, but you'll see here in a second that it's not integral to the way that that the rectifier behaves. Make sure we're still recording. Okay, good. So now let's talk about how this works. One main thing you'll see right off the bat is that this requires 4 diodes, as opposed to 2. So you gain something in this regard that you don't need a transformer. That's good, I guess. But you lose in terms of having to now use 2 more diodes. Okay, so let's take a look at how this works. Essentially, the diodes are positioned in this sort of anti-parallel way such that when the polarity is like this, 2 of the diodes conduct, D1 and D2, providing a path for current that flows from right to left across the load resistor. Remember, this is, I don't know if I explicitly stated it, but this is the load right here. The other 2 diodes will block. Now, what happens when the polarity is reversed to this? The diodes that were conducting before are now blocking. Diodes 3 and 4 are now conducting. And the most important thing is that the direction of the current across the load is the same as compared to the previous. Okay. So the main advantage of the bridge rectifier is that there's no need for a center tap transformer. Right, the transformers can often be bulky. They can often be more expensive than the other components that you're using. And so there's an advantage to being able to cut that. There are some disadvantages. The series connection of two diodes will reduce the output voltage. So let's take a look right here. When the diode is when the rectifier is conducting, I'm going to draw a line here that shows the entire path of the current. So it looks like this, looks like this, looks like this, looks like this. Okay, so if I were to write out KVL for this, I'll call this VS. These will have a voltage VD across them, which will be approximately 0.7 volts. So we'll write out KVL for this. And what we will end up with is that VO is equal to VS minus 2VD. Okay, and so that is shown. I don't have an input-output waveform. Where is it? Gotta find this. All right, I guess I don't have a graph of this on here. Weird. All right, well, that is the case, though. Now, let's also talk about the peak inverse voltage. So the peak inverse voltage will be less per diode as compared to the center tap. So for the center tap version of this, the peak inverse voltage across each diode was 2 Vs minus Vd. Because now each path has two diodes as opposed to one, there's an advantage where the peak inverse voltage is actually being split between the two diodes, which reduces its magnitude. So instead of it being 2 Vs minus Vd, it's 2 Vs minus 2 Vd, which can be simplified down because we have to divide by both the diodes to Vs minus Vd. So the good news is that when we're using the bridge rectifier, the expectation for the blocking capability of the diode is that we use is less. So if we go back to the other example where the Vs was 20 volts, okay, now we only need a diode that is able to block 19.3 volts as opposed to 39.3 volts. Okay, so the next topic that we're going to discuss is how a filter capacitor can be used along with the rectifier. Now, this is a topic that's going to take several different versions. But let's start off by looking at the simplest version, which is shown here. It's the source, half-wave rectifier, and then a simple capacitor serving as the filter. And then this is the load voltage here. So, we know that the pulsating nature of the rectifier output makes it an unreliable DC supply. Right, the ripple here is too much for, will not properly allow something like battery charging. So what we're going to do, and we saw this earlier on when we talked about the DC power supply, is we're going to use some sort of a filter, in this case, a filter capacitor by itself, in order to remove the ripple. And so let's look at the steps of this process and how the capacitor affects the system. So first step is that the source voltage is positive, the diode is forward biased, and the capacitor charges. So that's essentially taking us from right here all the way to right here. During this time, current's flowing in this direction, and the capacitor is charged. Now, step 2 is that when the source voltage is reversed, the capacitor can, the diode will be reverse biased, it will block, and the capacitor will not be able to discharge. So once the voltage drops, this part of the circuit will open up, and the capacitor will be isolated, meaning that it will maintain the charge across it. So steps 2 and 3 cover this part of the waveform here, but you'll note that the voltage across the capacitor stays unchanged because there's no path for it to discharge. If the charge stored within the cap stays the same, the voltage across it will also stay the same. Now, this is an unrealistic example, okay, because for any practical application, we would want this converter to be connected to some sort of load, right? There's really no point in having a power supply that doesn't power a load. And if we did attach a load, what we would see is that in steps 2 and steps 3, there would be a path for the current to discharge through the resistor being turned into heat or whatever work it is used for. And that will cause the blue line to drop, right, because of this discharging. The value of the resistance will determine how quickly that voltage will drop off or how quickly it will discharge. So now let's look at a version of this problem that's sort of 1 step, 1 degree more difficult, where we have our source, we have our diode, we have our cap, and now we are adding our load resistor. And we want to analyze how this circuit will work. Okay, so in order to do that, we need to, and don't grimace, I know that Laplace transform is always means a problem that's going to require a little bit of extra work, but so we're going to have to apply Laplace transform in order to look at the transient response of the rectifier. Now, the first step in doing that is to split the circuit's operation into 2 different states. So we have one state for when the diode is conducting, and for the purposes of this problem, we'll either be using an ideal diode model or a constant voltage drop. So when the diode is conducting, what we'll see is that the voltage here will be directly applied across the parallel combo of both of those. Now, state number 2, so this is state number 1. State number 2 will be when the diode is blocking. The source here will have no effect because it's isolated from the rest of the circuit, and we'll simply be looking at the interaction of the cap and the resistor, which we know will entail the capacitor discharging current through the resistor. So what are these equations down here? Again, I apologize for all this extra junk. I will try to clear this up by next time. So for circuit state number 1, we can see that the output voltage will be equal to the input voltage minus the voltage drop across the diode. Pretty straightforward. For the second state, we'll see that VO of t will be equal to whatever the peak voltage is of the output times e to the negative 1 over RC times t. This is an exponential response similar to what we have seen in previous problems. This equation here is just I rewrote what was sort of covered up in the by the weird symbols. Now, this equation right here, we haven't solved for that yet. I'm giving you the answer, but now we want to take a step back and ask ourselves, well, how do we get that answer? So in order to do that, we are going to examine this analysis on a more granular level. So the first step, analyze the circuit for state number 1, which is shown here when the diode is forward biased. And what we'll see is that IL is equal to VO over R, right? That's just applying Ohm's law right here. And we know that KCL tells us, I'll put KCL right here. KCL tells us that ID will be equal to IC plus IL, as shown. Now, what we can do, I'm just crossing out the part that's a little bit muddled. We can plug this in right here, and we can replace IC with C times D VI dt, which is the VI, well, it represents the VI characteristic for the cap. Now, you could ask me, well, why is this VI and not V out? And the reason for that is that V out will be equal to VI minus a constant. And so if we're taking the derivative of that, the constant will go away, which means that that dVi will be the same as dVo. Okay. Now, the last thing, we'll write this KVL expression telling us that V out is equal to V in minus the voltage across the diode. Okay, but analyzing circuit state number 1 is significantly easier than analyzing circuit state number 2. So for circuit state number 2, we have what looks like, well, I'm not going to say what looks like, it is a simpler circuit, R and C in parallel. But now we want to characterize the behavior for this state. Now, a couple different expressions that we can use. We can apply Ohm's law. We know that V out will be equal to R times IL. We can also apply KCL. We know that IL will be equal to negative IC based on the direction that these are set. Both currents are flowing out of the node, therefore the sum of them will be equal to 0. So you could also say IL plus IC equals 0. Okay, now we're going to use a combination of circuit and Laplace analysis to solve for VO in terms of the initial condition in time. And how are we going to do that? Using this right here. All right, so now you can see I've switched over to OneNote. And we are going to, we're going to do the same Laplace analysis that was shown in that previous slide, but we're going to do it by hand. So let's start off by writing out some of the equations that we know. Okay, and again, we're focused on state number 2 right now. We know that V out is equal to R times IL. And we also know that V out is equal to negative R times IC, because if we take this substitution right here, IL is equal to negative IC as dictated or given to us by KCL. Okay, we can also make one more substitution here since we have it in front of us. So V out is equal to negative R times C dVo dt, right? And all we're doing from this step to this step is just right, we're applying the VI characteristic for a capacitor. Remember that VO is the voltage across the capacitor. So I'll say write out relevant equations and substitute, because that's what we did here. All right, next. So next what we're going to do is we are going to put this in standard form. Sorry, my handwriting is getting messy. Put this in standard form. And apply Laplace transform. Okay, so what the standard form is going to look like we will have, and we're deriving this from the equation here. So what we will have is VO plus RC dVO dt equals 0. Now we can apply our Laplace to both sides. And what that will give us is, so this was originally really VO of t. Okay, we didn't necessarily write it out every time. But now what we'll have is capital VO of S plus RC. And then here is where we have to apply the Laplace transform for the derivative of a function. That's going to give us SVO of S minus the initial condition of VO. Okay, so I'll just write a quick reminder here that the Laplace transform of the derivative of a function, right, is equal to that function times S times f of S minus the initial condition of that function, whatever f of 0 is. Okay, so next. Okay, next. So we want to solve, right? We want to solve for VO, right? The next thing, or maybe I'll write here our goal is to solve for VO of t. So how do we do that? We will need to consolidate our variables. All right, so let's try to consolidate all of our VOs. One thing that I will point out is in many previous examples, we've assumed that the initial condition is non-existent. Here, we will not be able to make that assumption. The initial condition will exist, most probably. Well, it will. I'll tell you right now, it will. Okay. So, let's rearrange here, and what we'll end up with is VO of S times 1 plus RC. And what we've done is just taken the coefficients of this and this, and I forgot my S. Now, what that will be equal to is on the other side, we'll move the initial condition over to the other side. And so that will leave us with a positive RC times V output initial condition. All right. Now, if we wanted to, real quickly, we can well, first let's take a look at well, normally in these types of problems we want to have S isolated because the vast majority of the forms or the elements in the Laplace transform table have S without a coefficient. So since we know that is usually going to be the case, we'll go ahead and multiply both sides by a 1 over RC. which then will get rid of this, it'll get rid of this, and it'll make this 1 over RC. So what we end up with is VO of S times S plus 1 over RC equals V out of 0. Okay, now the last thing that we need to do in order to solve for our V out of S is just move that over to the other side, which will leave us with V out of S is equal to V out of 0 times 1 over S plus 1 over RC. Now, the good thing is that we have an element in the Laplace transform table for this, right? We know that the inverse Laplace of 1 over S plus alpha is equal to e to the negative alpha t. And so doing our inverse Laplace transform will be pretty easy. So we're on step number 4. Step number 4, apply inverse Laplace to yield the answer. So if we apply our Laplace transform to everything up above, what we will end up with is VO of t is equal to the initial condition VO of 0 e to the, which I can also write as exp, minus 1 over RC times t. And that is the same answer that we showed a second ago on the PowerPoint. So now I'm going to switch back over to that. Okay, so now we're back on in PowerPoint, and we can see that we ended up with the solution that we had. So the solution we got from OneNote is the same as the solution that we see right here. Now, what is V out of 0? What is the initial condition? Remember that we're talking about the initial condition for state number 2, not for state number 1. So that's different. And the trade-off between state number 1 and state number 2 will occur when VI is at its peak. And therefore, we will call this VI peak. Well, actually, sorry, that's going to be a different number. We're just going to call it VO peak. All right. And so, again, right, that gives us, sorry for this junk down here, but the main takeaway is that the solution we see here is the same as which we derived previously. Now, if you take a look at these graphs, this shows physically what's going on. So during the charging interval, which is essentially the green, okay, what we see is the charging interval is very short. During the charging interval, the voltage here is applied across the resistor and the capacitor, which causes it to charge, okay? And this, so up here we have the voltage, down here we have the current. And so you see that there's a very significant current spike during the charging interval that corresponds with the energy transfer that's required to charge. This is the current across the diode. There is no current across the diode during the discharging interval because during the discharging interval the diode is open circuited. Now the current across the load is going to be simply equal to VO divided by R. And so you can see the shape of this very closely resembles the shape of this up above. Now, one value that we are concerned with is this gap here, which is called VR, or the ripple in the output voltage. Because now the capacitor is able to discharge through the resistor, it's not going to have this completely flat line as we saw in that one previous example. So part of this design problem is going to be properly sizing the capacitor and the load such that we have an acceptable ripple, one that is small enough that it still allows proper charging or whatever application it's being applied to, but one that's also practical in terms of what capacitor sizes we have available and how much money we're willing to spend, or resources we're willing to use. So a couple of observations here. We already saw that the diode conducts for a brief interval near the peak of the input of the sinusoid, and supplies the capacitor with charge equal to that lost during the much longer discharge interval. The latter is approximately equal to T. What that means is that the discharge interval is almost equal to that of the period, right? This is very small right here. And this is very long and really almost equal to the whole period, where the whole period would technically be from here to here. Second observation is going to be, if we assume an ideal diode, conduction begins at time t1, at which the input Vi equals the exponentially decaying output Vout. So what is that saying? That the voltage decays and then charging begins where those two lines intersect, where the blue and the black intercept. That is when the diode will start conducting, because, right, the voltage on this side of the diode will drop below what the voltage is on this side of the diode. Diode conduction stops at time t2, shortly after the peak of Vi, which is exactly which is its peak. So if we have, you can see it here. So we have T1 and we have T2. During the diode off interval, the capacitor C discharges through the resistor, causing an exponential decay in the output voltage VO. At the end of the discharge interval, which lasts for almost the entire period T, the voltage is equal to VO. So VO at the end of the period is equal to the peak minus the ripple. Again, that's backed up by what we saw over here, right? The voltage at the end, I've drawn so much it's kind of hard to put anything more here, but you can see the voltage at the end of the interval is going to be equal to the peak minus the ripple, which we already talked about the ripple right here. When the ripple voltage is small, the output is almost constant and equal to that of the peak of the input. The average output may be defined as shown down here. So again, I apologize. This is one part where the math has gotten a little bit distorted, but the main takeaway, I'm going to skip straight to the end here, is equation 428, which says that for very small ripples, the ripple will be approximately equal to the peak times the period divided by the R and the C values. So this equation right here does not apply to every case. But what it does is it applies to cases where the ripple is relatively small. So if you eyeball, look at the ripple, see that it's again relatively small, and you want to come up with a numerical value for it, you can use this equation right here. So this will be included on your cheat sheet, and you'll see it's going to come in handy for a number of different types of problems. There's several different versions of this equation. 429 allows you to put it in terms of frequency, but to tell you the truth, they're all just different versions of the same equation. Now observe that these equations are all dependent on the fact that the ripple must be much, much smaller than the peak of the wave. So you definitely, most definitely can, it'll work for something like this. It will not work for something like that, where the discharge interval goes very deep. There's several other equations that are important. Equation 430, if you can see through all this junk down here. If you download a copy of the PDF notes from the website, you'll see it's a lot clearer. You can use equation 430 to, again, estimate the length of the conduction interval if the ripple is very small. All of these equations you're seeing on these last few slides, all of them assume that the ripple is very small. Okay, so this gives us the peak-to-peak ripple. This gives us the conduction interval. Okay, and then we move on to limiter circuits. So this seems like a good place to stop. So we'll cut it here for today's lecture.